Okay, question 6. The diagram shows a particle about to collide elastically with the wall. So that means that the momentum afterwards is going to be exactly the same, but in the opposite direction. So the momentum to the left, generally we say to the left is negative. And so we say that the particle is moving with a velocity v in that direction, and it has a mass m, so it has a momentum of minus mv. And once it hits elastically and collides with the ball, it's going to bounce off in some direction that way, and its speed's going to stay the same, its mass is going to stay the same. This direction is positive, so that would be mass times velocity. Now the change in momentum is mv minus mv, which is 2 mv. Now, what you have to remember is we are looking not for adding these momentums up. We are looking for the change in momentum. So if you add these momentums up, just how they look, it may end up being something like that or like that. Now, what we have to remember is we are looking for the change in momentum. So the final momentum is mv. So that is a momentum that starts off that way. So we want to see an arrow for mv going to the right, okay, sloping to the right top corner of your page, just like that there. Now, if you look at this, no, we don't have an arrow facing that way. So we have got one facing that way and one facing that way. Minus the initial momentum. Now the initial momentum is minus mv. Okay, so that's facing this way. But when we take away this initial momentum, that minus and that minus end up being a plus. Okay, so what we get is an overall vector pointing in the opposite direction downwards. So look at the direction. It's facing to the bottom right hand corner of the screen. So now we've got to look for an arrow facing to the bottom right. So we had this one, this one and this one as the final momentum. Now the initial momentum has to face to the bottom right. Now that is not doing that. Okay, so if you didn't look out for that sign there, you end up with this answer here. So the change in momentum is in the right hand direction, not in the vertical direction. Okay, right. So what we've got is the final momentum minus the initial momentum gives you an overall momentum in towards the right. And when we look at that, mv minus mv gives us 2 mv. Okay, and it is in the direction in which the perpendicular to the wall, not parallel to the wall. That does not make any sense. The change in momentum here is parallel to the wall. The wall does not change the direction vertically. Okay, it changes the direction horizontally. Here the ball is going upwards beforehand, and it still remains going upwards afterwards. The only direction that has changed is the ball was moving to the left, now it's moving to the right. So therefore, change in momentum is to the right. Question 7, a Brownian motion. This is what Einstein confirmed of the work that Stefan Boltzmann did many years before. that particles are moving randomly, they are colliding continuously in random directions, and the motion that he kind of explained was Brownian motion, pollen grains in water, and he saw them vibrate. Those vibrations were due to we've kind of mimicked the experiment with smoke. So smoke in air rather than pollen in water, and you see the same effect. Okay, so the smoke particles colliding with the air particles explains Brownian motion. Right, question 8. The pressure inside the bicycle tire. You've got volume, you've got the pressure, and you've got the temperature. So you've got P, V, T. Straight away I'm thinking I need to use this formula or the one with N and K in it. Because if I ask for a number of moles, I'm writing that down straight away. I'm rearranging it. Pressure, 3.2, it's in meters cubed, that's fine. That's the pressure. The pressure is in pascals, 3.2 times 10 to the 5. The volume is in meters cubed, that's correct, 1.9 times 10 to the minus 3. The temperature is in Kelvin, that's 285, and the gas constant is 8.31, that'll be given to you. And rearrange, put the values in to your calculator, you get an answer of 0.26. Now, there are a number of ways sometimes to do these questions later on when we're comparing before and after. So calculate the new pressure in the tire, assuming that the volume is unchanged, and giving your answer to an appropriate number of significant figures. So it says, after the bike has been ridden, the temperature has increased to 295. The temperature before was 285. Okay, so it says that the volume of the tire is unchanged. So if the volume of the tire is unchanged, and we know that this expression here, if the temperature is unchanged, if the volume is unchanged, the number of particles inside the volume is unchanged, then pressure is directly proportional to temperature. So what we can write down is either P1 over P2 is equal to T1 over T2, or we can write P1 over T1 is equal to P2 over T2. Okay. You could have put it as all these numbers in, but they would have cancelled out. So rearranging, and that gives you a pressure of 3.31 times 10 to the 5 pascals. Okay, describe one way in which the motion of the molecules of air inside the bicycle tire is similar. One way is different. Particles are moving randomly at both temperatures, so the temperatures increased. Still an ideal gas in a way. The particles are still, even if it was an ideal gas, particles do move in random directions across all temperatures. The second one, we know that as the temperature increases, the average kinetic energy of the particles also increases. That's directly related to the root mean square speed. So you could say that at a higher temperature, the particles on average are moving faster.